Hello everyone, and welcome back to this NPTEL lecture series on cycloaddition reactions. So this is lecture number 11, and in the last lecture we talked about 1,3-dipolar cycloaddition reactions, and we also discussed about 1,3-dipolar cycloaddition reaction of ozone with various alkenes and how ozonolysis can cleave a double bond through this 1,3-dipolar cycloaddition reaction. So today we will move to another dipole called nitrones. So these nitrones are very interesting class of compounds, and they are nothing but the oxidized version of imines. If you have an imine and if you do the oxidation of the nitrogen of the imine, then it is called nitrone. For example, so this is an acyclic imine, and if you do the N-oxide of this acyclic imine, then this is called nitrones. And likewise, you can also have a cyclic imine, and if you do the oxidation of the nitrogen, and this N-oxide is called corresponding cyclic nitrones. Likewise, there are quite a few sugar-derived cyclic nitrones. Obviously, they are chiral, and you can see here this is a 5-membered one, and this is a 6-membered one. So one can easily make all these nitrones in a few steps. So now let us see how these nitrones are prepared. The easiest way to prepare a nitrone is you take an aldehyde and then treat with an oxime. Okay, take an aldehyde and treat with oxime. So then in principle it can lose a molecule of water to form the corresponding acyclic nitrone. One can also prepare nitrones from amino acids. For example, if you take proline and then treat with the catalytic amount of sodium tungstate and excess hydrogen peroxide, it can undergo a decarboxylative oxidation to form the 5-membered nitrone. And one can also easily oxidize the substituted hydroxylamine. For example, if you take such hydroxylamine derivative and then oxidize with mercuric oxide, so that can undergo a sort of dehydration to give the corresponding nitrones. This can be extended to cyclic compound. For example, N-hydroxypyrrolidine, if you treat with mercuric oxide, so that can give the 5-membered nitrone. Then if you have a ketone and a leaving group at a distance where the ring size can be 5 or 6. So you take this ketone and then treat with hydroxylamine. So in situ what happens, first it forms the oxime, then the lone pair on the nitrogen intramolecularly attacks the carbon bearing the leaving group in an SN2 fashion to form the corresponding nitrone. So this way 5-membered, 6-membered, 7-membered nitrones can be easily made. So what you need is you need a carbonyl group and a leaving group and a proper tether. So once you have 3 or 4 tether, then it is easy to form the 5-membered or 6-membered nitrones. One can also make several sugar derived nitrones. For example, this OTBS protected N-oxime can be easily made from monosugar, and you can also see there is a leaving group. Now the moment you use fluoride source, for example, if you add TBAF, as you know, tetrabutyl ammonium fluoride is known to remove the TBS group. Meanwhile, what will happen, the lone pair on the nitrogen intramolecularly do an SN2 reaction and then kicks out the mesylate. So this will give directly a nitrone. Okay. One can also prepare this nitrone. For example, if you start with D-ribose after making the monoastronide and converting the primary alcohol into tosylate, okay, basically you need a leaving group. Now if you take this lactol and then reflects with hydroxylamine hydrochloride in the presence of base like triethylamine, it forms first in situ, it forms the corresponding oxime, and the lone pair on the nitrogen does the SN2 reaction, and followed by loss of proton gives the corresponding 6-membered nitrone. So, this is very easy. In one step one can prepare the nitrone from directly this type of lactol, also having a leaving group. And there are other methods also to make nitrones. Say for example, if you have a double bond, a terminal alkene and also an oxime. Now, if you treat with reagents like iodine, NBS, phenylselenyl bromide and mercuric acetate. So, basically what will happen, so this iodine or NBS or phenylselenyl bromide, first it will form the corresponding iodonium or bromonium or phenylselenium. The 3-membered ring it will form, then the lone pair on the nitrogen intramolecularly will attack and open this the 3-membered ring to form the corresponding 5-membered or 6-membered depending on N. You will get 5-membered, 6-membered or 7-membered nitrones. Okay. So, these are some of the methods where one can easily prepare nitrones. Now, let us move to the regiochemical and stereochemical outcome of 1,3-dipolar cycloaddition between nitrones and other dipolar-ophiles. So, the stereochemistry of this 1,3-dipolar cycloaddition depends on the nature of the dipolorophile, whether the dipolorophile is electron rich or electron deficient, that determines the regiochemical outcome of the 1,3-dipolar cycloaddition. For example, if you take nitrone, you can see here, so this particular carbon is electron deficient or it has large LUMO coefficient, and this oxygen is electron rich, or one can say it has a large HOMO coefficient. And when you take an alkene, which is a dipolorophile, now the alkene has electron donating R group. Okay. Then what will happen? So, this is the electron rich end. So, the reaction will take place between these two carbon and oxygen and this carbon. So, that will lead to this regioisomer. Okay. With electron rich alkene, mostly you get this regioisomer. Now, let us see what will happen if you have electron withdrawing group attached to the dipolorophile, attached to the alkene or the dipolorophile. Same nitrone. Now, this carbon is electron deficient. Okay. Then obviously the reaction will take place in the opposite way. So, that means you will get the opposite regiochemistry. If you have electron withdrawing group attached to the dipolorophile, then you will get this regioisomer. Okay. So, the regiochemical outcome of 1,3-dipolar cycloaddition between nitrone and dipolorophile depends on the nature of the substituents attached to the dipolorophile. Okay. Now, let us see. So, a simple nitrone. So, this is formed between benzaldehyde and then that methyl hydroxylamine. So, now if you treat with this butyl vinyl ether, so this can undergo 1,3-dipolar cycloaddition to form this regioisomer predominantly. Okay. And one can ask, compared to O-butyl, CO2Me is electron withdrawing, but it is not that electron withdrawing. So, the regiochemical outcome does not differ much. So, this is the major regioisomer you get when you do this 1,3-dipolar cycloaddition with methyl acrylate. However, if the electron withdrawing nature changes, and if it is more electron withdrawing like the one here, sulfone, then you will see the regioisomer shifts in favor of the other one. Okay. So, this is a major product in this case, and that is almost you can see 2:1 ratio. Okay. And if it is very strong electron withdrawing group, then you will get only the other isomer. So, one can also in situ prepare nitrones. For example, this oxide, if you treat with alpha beta unsaturated ester, now what will happen? The lone pair on the nitrogen undergoes to 1,4 addition to the methyl acrylate. So, that will in situ generate the nitrone. So, once it generates nitrone in situ, it can undergo a 1,3-dipolar cycloaddition with one more molecule of methyl acrylate to give this very interesting spiro system. Okay. So, now as I said, if the electron withdrawing nature of the group which is attached to the dipolarifier is very high, then you will see reversal in the regioselectivity. So, we saw with sulfone the selectivity moved in favor of the other isomer. Now, if we have more powerful electron withdrawing group nitro, then you get exclusively this isomer. Okay, nitro is very powerful electron withdrawing group. Or instead of one ester, if you have two esters, then that will make sure that this carbon is electron deficient, and obviously you get only this regioisomer. Okay. So, that is how one can decide the regiochemical outcome of 1,3-dipolar cycloaddition between nitrone and dipolarifiers. How about stereochemical outcome? Compared to 4+2 cycloaddition reaction, in the case of 1,3-dipolar cycloaddition, the secondary orbital interaction is very small. When the secondary orbital interaction is very small, as a result, what will happen? The stabilization due to the secondary orbital interaction is almost negligible. Okay. When that does not happen, then automatically this 1,3-dipolar cycloaddition will lead to the more stable or thermodynamic exo product. Okay. So, that is what will happen if you take this nitrone and then treat with acrylonitrile, and as we have discussed, assume that the dipolarifier approaches the dipole, that is nitrone, from the bottom phase, and if it gives exo product, so this is what you will get. Okay. So, I will leave for a few seconds for you to understand. Nitrone is here, and then your dipolarifier comes from the bottom and your cyanide is outside like this. Okay. Because we are going to get the exo product, and this is what you will get. Okay. So, what is important is, in the case of 1,3-dipolar cycloaddition, the secondary orbital interaction is almost negligible, because of which the thermodynamically more stable exo product is obtained as the major product. Okay. Now, let us take another example, the acyclic nitrone, and then treat with methyl acrylate and see the transition states. So, there are two transition states I have written. So, this is the endo transition state and this is the exo transition state. As we have discussed, it will give mainly the exo product, and this endo approach will give this product, which can be redrawn like this, and the exo product can be redrawn like this, and this is the major product in this 1,3-dipolar cycloaddition reaction. Now, it is very easy to analyze the stereochemical outcome of 1,3-dipolar cycloaddition of nitrones. And in the previous example, we saw the substituent on the nitrone is phenyl group, but it is a linear nitrone, acyclic linear nitrone. What will happen if we have a cyclic nitrone, and the cyclic nitrone also has some additional functional groups? The stereochemical outcome is mainly influenced by the dipole and dipolorophyl. Okay. If you have substituents present in the dipole, then they will influence the stereochemical outcome. Okay. Now let us see how substituents present in the dipolorophyl determine whether you get endo product or exo product. Okay. So let us draw this transition state. So this is the cyclic nitrone, and you can see the R group is away from the nitrone. That means this is exo. And in this transition state, you can see the R group is below nitrone. So that means it is endo. Okay. So what happens when you have a substituent on the dipolorophyl? That substituent will determine whether you get exo or endo, and as we know, it will give mainly the exo product. Okay. Now, if you have substituents present in the nitrone, then what will happen? See, for example, you can see there are two substituents present in the nitrone. So this cyclic nitrone has two substituents. Now, the same way as we know, the dipolorophyl prefers the exo approach. Okay. So this is the transition state. But this dipolorophyl also comes opposite to the two substituents present here. That is anti to the two substituents present in the dipole. Okay. This is called exo and anti. Exo with respect to the dipolorophyl, anti with respect to the substituents present in the nitrone or dipole. And one can also write the endo and anti. So this is endo and this is anti to that. And this is the most preferred one. So when you have substituents on the dipole and substituent on the dipolorophyl, the most favored transition state is exo anti, and accordingly you will get exo anti products. This is what you should remember. Okay. Now let us look at few examples. Take 6-membered cyclic nitrone and then treat with propene. So it gives the exo products, and this can be easily justified. And once you have that, you cleave with LiH. Lithium aluminum hydride is known to cleave the NO bond. When it is cleaved, you will get NH and OH. So this is what you get, and that is a natural product called cedridine. And now you can see here this is a racemic compound. Okay. So how will you get chiral one? Okay. Yes, it is possible. Suppose if you have a chiral substituent present in the dipolorophyl. Here you can see you have a chiral sulfoxide, and this chiral sulfoxide will decide, okay, the stereochemical outcome. Here it is relative, this is absolute. Okay. So now you cleave the NO bond and followed by remove the chiral auxiliary, you will get the plus isomer of this natural product. Okay. By attaching the chiral auxiliary in the dipolorophyl, one can get exclusively or predominantly one isomer. Okay. Likewise, one can also have chiral substituents on the dipole that can also decide the nature of stereochemical outcome of 1,3-dipolar cycloaddition. So now see, the nitrone has two chiral centers already fixed, and this is beta. So what happens whenever you have a cyclic nitrone? The dipolorophyl will come exactly opposite to this particular chiral center. This is what we discussed. You remember, when you have nitrone and it has two substituents, then the dipolorophyl will come opposite to that. Okay. So now these two are esters, that means this will be exo. Okay. So what you get is exo anti product. So what's the product you will get? So you can see, so this is exo and this is anti, because the whole thing comes away from this oxygen. That means these two bonds will be alpha. Okay. So, this way one can easily introduce 3 more chiral centers, 1, 2, 3. Okay. The existing chiral center in the nitrone determines the 3 more chiral centers. So, now you can cleave the NO bond. When you cleave the NO bond, what you get is you get the corresponding you get the amine as well as alcohol. I have rotated this CC bond. Okay. So, when I rotate the CC bond, the ester comes here, and now this lone pair on nitrogen attacks, what you get is a 5-membered compound. Okay. So, once you have that, then this can be converted into 2 natural products in few steps. Okay. Then this is a very interesting compound, a nitrone having 3 chiral centers. Already it has 3 chiral centers. What is the first step? Addition of allyl magnesium chloride. Here, not only the dipolarified will come opposite to this particular stereo center, if you add any nucleophile to this nitrone, that nucleophile also will add opposite to that bulky benzyl group. Okay. That means, when you add this allyl magnesium chloride, so what you get, you can see here, the allyl group will come from the beta side. So, you can see that beta. Then you get the corresponding N-oxide. Then you get the corresponding cyclic hydroxyl amine. So, this is the intermediate you get. Okay. This upon oxidation with manganese dioxide, then you generate a nitrone on the other side. Okay, that is the only place it can form nitrone. So, oxidation of this N-hydroxypyrrolidine gives the corresponding nitrone. So, now if you treat with toluene or if you heat it, there is a dipole and this is the dipolarified. So, this can undergo an intramolecular 1,3-dipolar cycloaddition. Okay. So, that will give you this isomer. Please try to write the transition state to get this particular tricyclic compound. So, now when you cleave this NO bond under hydrogenolysis condition, not only the NO bond will cleave, you can also remove the benzyl group. So, that will lead to this very interesting polyhydroxy compound. Okay. Basically, if you look at this, in 4 steps from nitrone, you could get very complex natural product. Okay. And of course, this I have already discussed. Just to give one more example, see here, XO is a major product. So, once you have this compound, we can also extend this 1,3-dipolar cycloaddition to cyclic enol ether. Already we did with butyl vinyl ether. So, now you can do with a cyclic vinyl ether. So, that will give you this as the major product. Again, you remember, XO product is the major product. And you can also do this with ethyl vinyl ether, that also will give the corresponding XO product. So, briefly I talked about the intramolecular 1,3-dipolar cycloaddition reaction. So, now look at this particular case where you can see if you have this isomer and that can be redrawn like this, then if this undergoes a 1,3-dipolar cycloaddition and it happens like this, that will give you this tricyclic compound. So, now you can cleave this NO bond. When you cleave this NO bond, you will get corresponding amino alcohol. So, what you should know is this 1,3-dipolar cycloaddition reaction between nitrone and alkene followed by hydrogenolysis can give amino alcohol. So, if you start with the chiral nitrone and then do this two-step sequence, you will end up in getting chiral amino alcohols. So, this is a very interesting method to make chiral amino alcohols. If you look at nature, we have a limited number of naturally occurring amino acids which can be converted into corresponding amino alcohols. Here you can use dipolar cycloaddition followed by hydrogenolysis to get a range or a library of new chiral amino alcohols. So, another example where you can see 1, 2, 3 new chiral centers can be fixed, though it is a racemic compound, but in principle one can fix 3 new chiral centers. Now, cleavage of this NO bond will give the corresponding amino alcohol, and if you use LAH, the ester also will be reduced. So, you get dihydroxyamine. Okay. If you take citronellol, so this is a monoterpene, it is called citronellol. And then treat with methyl hydroxylamine followed by heating, you will get this very interesting bicyclic compound. And this goes via this type of transition state, and that will give you the corresponding isoxazolidine, and one can cleave the NO bond to get the corresponding amino alcohol. So, from a monoterpene you can get an amino alcohol in 2 steps. Here is another simple example where you have CH2OH and ester on both sides of alkene. So, now if you do a 3+2 cycloaddition, you can see you have an ester here, you have CH2OH, and as I said, we form 3 new chiral centers, and now you can make this hydroxyl as mesylate and then do a hydrogenolysis. Okay, when you do hydrogenolysis, it cleaves the NO bond to get the corresponding amino alcohol. Before that, you converted the primary alcohol into mesylate. So, what will happen now, the nitrogen intramolecularly will displace the mesylate through SN2 reaction, and that can be used to make a natural product called supinidine. Okay. So, there are many such interesting conversions based on nitrone cycloaddition to several natural products. So, you can look at this example where you can see here you have a hydroxylamine and a double bond. Okay. And this hydroxylamine, when you treat with an aldehyde like this, and it can undergo condensation to form nitrone like this. And you have nitrone, and you can draw a very nice transition state. So, this is how the intramolecular 1,3-dipolar cycloaddition will take place, and now if you cleave this NO bond, you will get corresponding NOH. Before that, hydrolyze the acetate using potassium bicarbonate, convert that into mesyl group, then you do the NO bond cleavage. So, then what will happen, the whatever mesylate comes out, the lone pair on the nitrogen will attack here, and this is mesylate. So, you get the 5-membered, that is pyrrolidine ring. Okay. So, basically if you look at by doing 2 or 3 more reactions, one can get very nice bicyclic, tricyclic compound, and that is the core structure present in many natural products. In this case, it is called indolecidine 209B. Now, look at this little bit complex monosugar. Okay. So, this is derived from L-arabinose in a few steps. Now, if you treat with methyl hydroxylamine, okay, so that should form this nitrone. Already we have seen a similar example starting from citronellol. Okay. So, now you have more chiral centers, okay, and this can undergo an intramolecular dipolar cycloaddition and through this transition state, and when this happens you will get this product. Okay. So, now one can cleave the NO bond and further functional group transformation, this intermediate has been converted into the natural product called pleosporal A. Now look at this example. It's a acyclic nitrone and then do 1,3-dipolar cycloaddition. Now if you cleave this NO bond and do a reductive amination with this aldehyde, you will get the corresponding alpha amino acid. Okay, if you see this amino acid, it is hydroxyproline. Okay, if you use chiral catalyst, then you can make this chiral amino acid. So there are many nitrone cycloaddition where chiral catalysts have been successfully used. Okay, now let us look at this example. So this is a very interesting example. You have a ketone, and then when you treat with hydroxylamine, so it will undergo first condensation to form the corresponding NOH. Okay, so what will happen? You will get the corresponding oxime, and you can see here you have a leaving group that is chloride. So intramolecularly the nitrogen will attack, and then that will form the 5-membered nitrone. Then that 5-membered nitrone also has the dipolar file. Okay, 1, 2, 3 and the double bond. So what will happen once the nitrone is formed, this will undergo an intramolecular 1,3-dipolar cycloaddition to get this nice tricyclic compound. Last example of nitrone cycloaddition reaction, very interesting. So if you look at this particular compound, you have a leaving group that is tosylate, and the way the nitrone is formed is just use the lone pair on the hydroxylamine derivative. Now push this and eliminate the tosylate. When you do that, you generate the double bond and you also generate the nitrone. Both are generated in situ. Okay. So now this can undergo an intramolecular 1,3-dipolar cycloaddition to form this tricyclic compound. Okay. Once you have that, then you can do the NO bond cleavage to get a bicyclic compound, and that can be further utilized in the synthesis of natural products. So what we have done today is to give a brief overview. We know how nitrones can be prepared. Then we discussed about the regiochemical and stereochemical outcome of 1,3-dipolar cycloaddition between these nitrones and various dipolar and we also discussed the application of this 1,3-dipolar cycloaddition followed by some functional group transformation to some very interesting natural products. Okay. So what we will do in the next class, we will talk about another interesting dipole called carbonyl halides and how carbonyl halides can be successfully used in 1,3-dipolar cycloaddition reaction. Okay. See you next week. Thank you. Bye.